Good news, I would say, is that if you felt like Chapter 6 was getting pretty difficult, we're going to take a little step back as far as mathematical difficulty goes. I think you might find this chapter to be a little bit easier than the previous one. Anyway, so Chapter 7 is continuing our idea here of statistical inference. So in Chapter 6, we talked about point estimation. Which is where we were trying to find an estimator theta hat to estimate theta. So whatever our parameter was, we were trying to find a way to estimate that using our data. So kind of bridging the gap to what we're going to be talking about in this chapter. Kind of suppose I'm back in my usual situation in Chapter 6. I have a random sample from a normal population. And let's suppose for now that I know what the mean is. I know what the standard deviation is. I don't know what the mean is. And what we found there was that the maximum likelihood estimate of theta there, of mu there is x bar. So now suppose that I actually do an experiment, and I have n equals to 4. So I collect 4 data observations, whatever I'm talking about here. And there's those observations. And so the maximum likelihood estimate I get there is the average of those 4 numbers, 119.175. Okay, so just sort of conceptually, so that's my experiment. Suppose you guys each do the experiment separately. Maybe you're, I don't know, maybe you're taking the average height or something of students at Ohio State. I go randomly sample 4 students. You go randomly sample 4 other students. Are you going to get the same maximum likelihood estimate that I do? So the MLE is still x bar. But if you do the experiment and find 4 new people, are you going to get the same sample mean there from your sample? Probably not, right? Chances are that you will not. And that is, again, let's say there's always variability in doing an experiment. Okay, so the point is that the actual number, so my estimate from you was 119.7175. If you did the experiment, you would get a different value. You would get something different than 119.175. And so is that a problem? I guess the idea here is that a single point estimate, a single number, doesn't give us any information about the precision or the reliability of the estimate. It just tells us one possible number of what that thing might be. So the main idea of this chapter is that instead of using a single number, so instead of making just a single guess, a single number, why don't I instead give you a range of plausible values? So a range of values that might be good at estimating what this population mean is. Okay, so and by good I mean here that the interval that I give you has a high probability of containing the true parameter value. So the goal is that I want to create an interval here, maybe from A to B, where A and B are sample statistics. I can calculate those, and I want to choose those statistics such that the interval is likely contain the true value. So the probability that my parameter theta is actually in that interval is going to be some large value. So maybe 0.95 or 0.99. I don't know. It's going to have some high probability that the true parameter. So here's the true parameter. Has a high probability of actually being inside that interval. Okay, so let's introduce some terminology here, keeping in mind sort of this motivating example. Some terminology here is that I've written it out in this way. So I've written the probability of 1 minus alpha. You might think that's strange, but I've done that because these because alpha has a special meaning. So alpha is called the significance level. So this is something we'll come back to. Come back to this in chapter 8. So that's not something we need to worry about too much at this point. But 1 minus alpha is called my confidence level, and then for whatever that is, whatever 1 minus alpha is, that's my I have that percent of a confidence interval. So if alpha equals 0.05, for example, then I have 1 minus 0.05 times 100%, which is 95% confidence interval. So I'll be using CI a lot to abbreviate confidence interval. Okay, so that's good terminology we need to have down, but we haven't actually started addressing this problem yet. How do I go about finding such an interval? Okay, so let's again, going back to our example here, I have a random sample from a normal population where mu is unknown, but sigma is known. So we're going to start there. So does that seem realistic to you, that I would know what sigma is, but I don't know what mu is? Probably not, right? How would you know what the standard deviation was if you didn't know what the mean was? So this is not realistic. Well, we're gonna assume this for now. And we'll come back to this. We'll come back to this unrealistic assumption. So for now, if that bothers you, we'll come back to that. Okay. So anyway, here's our example. We have a random sample of normal of IID normal random variables. And we want to find a range of values for the true mean mu that are sort of consistent with the observed data, or give us a 95% confidence interval for the true mean. So we want to find an interval such that the probability that the true mean falls inside that interval is 95%. So kind of sticking with our notation from before, I want to find A and B such that the probability that the mean is between them is 0.95. Okay, so how can I do this? Well, a good place to start is definitely our point estimate from mu. So this is using what we saw back in chapter 6. So remember that the distribution of our sample mean. So remember the individual observations, the xi's were distributed as normal with mean mu and variance sigma squared. And the distribution of my sample mean then is also going to be normal with mean mu and variance sigma squared over n. So this is going back to chapter 5. Okay. So remember, this is the distribution of my sample mean x bar. It's centered at mu. I have a normal distribution for x bar. And so where, sort of thinking about the center of this distribution, where is 95% of the probability in this distribution? So that is, where is, let's find these values such that I have 95% probability in here, or 0.95 probability. And that means how much area is in each of those tail areas. Yeah, exactly. So I need those to add up to 0.05, and they're equal. So that means I have 2.5% in each of the tail areas there. Okay, so again, labeling these things, we want to find these numbers here such that, I think we used A and B earlier, right? We want to find A and B such that the probability that sample mean falls between, that the the population mean falls between there is 95%. So this picture is kind of your motivating example. So what I want to find, the probability that. So again, I want to find B such that this area below it is 0.975, or I could also find. Let me change colors. This area here such that this area is again 0.025. So in other words, I want to find some number A such that the probability of my sample mean being below that is equal to 0.025. So we're just going to use what we've done before to find that number A such that this is true. Okay, so how do I do this? Well, you're going to do the usual thing. I'm going to standardize this thing. So I want 0.025 to equal the probability that my sample mean, but I can standardize this now. So x bar minus mu divided by sigma over the square root of n is less than or equal to a minus mu. All right, I can standardize that thing. And so then what is the, see if you're awake this morning, what is the distribution of the thing in the blue box? Right, this is a z. This is my standard normal random variable because x bar was normal to start with. So I can go to the table, and if I want this probability to be 0.25, I can find that this is I need to be less than negative 1.96. So if you go to the table and look up the probability that a z, so this is because the probability that a z is less than or equal to negative 1.96 equals 0.025. This is kind of going back to the same calculations you guys did a number of times already on various homework assignments. Okay, so that's our first step. But again, I also need to find. So that tells me something about A here. I also need to know something about B. So I also want to find the probability. I want the probability that x bar is greater than or equal to B. Sorry, less than or equal to B. To be equal to 0.975, which means the probability that x bar is bigger than B equals 0.025. Okay, and a similar argument as what I did on the line above that, I can figure that out. So because this distribution is symmetric, so by symmetry, if I standardize this thing x bar minus mu over sigma over the square root of n greater than 1.96 will give me that probability. And this is because the probability that a z is bigger than 1.96 equals 0.25. Okay, so kind of very formally stepping through this this exercise here. So we're almost there. So again, remember remember our goal is to find A and B such that the probability that the mean is between A and B equals 0.95. So that's our goal, remember. And so what I found on that previous page is that this probability of 0.95 is equal to the standardized value of my sample mean is between plus and minus 1.96. So negative 1.96 x bar minus mu over sigma over the square root of n. So that's what we found from the previous page, is that if I'm between negative 1.96 and positive 1.96, that captures 95% of the area for my z variable here in the middle. Okay, and so now I just need to rearrange this. So again, notice I have a probability statement of something involving mu, and so I can just rearrange this thing to get that in the form that I wanted up there at the top. So if we rearrange, this is equal to the probability. I can just take the multiply through by sigma over the square root of n, so negative 1.96 times do the same thing on the upper bound there. Okay, and we're almost there. I gotta get rid of the x bar in the middle there, so now we have this probably that negative x bar minus 1.96, so a negative mu in the middle. Okay. And then we want a probability involving mu, not negative mu, so we can multiply through by negative 1, which again flips the direction of the inequality there. So that gives us that we have x bar minus 1.96 and we get the x bar plus 1.96 times sigma over the square root of n. Okay, so here's A and here's B. So again, remember this is equal to 0.95. Okay, so just kind of very formally showing you how we step through and arrive at those two numbers as our limits that give us probability of 0.95 between. Yeah, Mary?
When you multiply by the negative, why does x bar become positive but the 1.96 stay negative on that side?
Oh, yeah. So so that's because, well, so let's say if you have, for example, c is less than negative y is less than d, that means that negative d is less than or equal to y is less than or equal to negative c. So I'm flipping those around. So the x bar changes. The x bar changes sign, as does the second part. It's just I'm now interchanging those endpoints there. Good question. Okay. So there we have it. This is our this is how we can put together a confidence interval for the population mean in this case. So here's the numbers that were just given on that previous page, almost. But there's a slightly different terminology in here. So again, remember, I have this 1.96 in here. Which will give me a 95% confidence interval. So this is a 95% confidence interval for mu. But you might just as easily want a different level of confidence. Maybe you want 99%, maybe you want 90%, maybe you want 10%. And so in general, we can generalize this thing. So again, if I still have the same setup, so if I have a random sample from a normal population where I Don't know what the mean is, but I do know what sigma is. In general, a confidence interval is given by that formula that looks very similar to what we just derived on the previous slide. So it's x bar plus or minus something, and that something is this part right here. So that looks almost like what we had on the previous page, except for that z sub alpha over 2, right? So all that is, that's just going to be our notation for a value on the standard normal distribution that has probability of alpha over 2 above it. So on my standard normal distribution here, let's try that again. This is my z centered at 0. This value here is z sub alpha divided by 2. It's going to have area alpha divided by 2 above it. And so similarly, I'll have negative z alpha over 2. I'll have alpha over 2 below it. Okay? So we found in the previous example alpha was 0.05, and so we found that z sub alpha over z sub 0.05 over 2 was 1.96. But in general, you could do that for any value between 0 and a half, I guess, for any alpha level. And so the terminology here is that z sub alpha over 2 is called a critical value. So maybe I should ask, have you guys seen confidence intervals before? Have you heard of any of this stuff before? Is this totally new, or seen some of this before? Okay. If you've taken AP stats or anything like that, you definitely would have seen this kind of thing. Okay, so this is the formula for our confidence interval that will give us, again, a 100 times 1 minus alpha % confidence interval for the population mean. Okay, and then we won't talk. Well, before I get to that, note that I have two conditions that I need to use this formula. So again, if we look up here, it says that I need a random sample from a normal population, and then I need mean mu and known variance sigma squared. Unknown mean mu and known variance sigma squared. So I have two conditions here. The first is that I have a random sample from a normal population, and I know what sigma is. So again, looking at that formula, to be able to calculate this interval, I need to know what sigma is. And so both of these conditions, again, are very limiting. you might imagine. And just to put you at ease, since I know you're very nervous about this, we'll come back and we'll address each one of these. We'll address each one of these conditions. We'll relax these and show that we can still do something in those cases. Okay, so that's again our confidence interval. If I instead want something called a confidence bound, and again we won't spend a lot of time talking about these, but if you wanted either an upper or lower confidence bound, so that you didn't care what the upper end of this confidence interval was or the lower end, then you could calculate it similarly. So if I want an upper confidence bound, I don't care what the lower end point is, then I can use that interval, and I can do the same for a lower confidence bound. And note the only thing that's different here is the critical value. So it's z sub alpha instead of z sub alpha over 2. Anyway, we won't spend a lot of time talking about confidence bounds. But I wanted to put that in there for completeness. Okay, so we have not yet said how to interpret a confidence interval. So we found what our formula was and showed how to get that and how to do it in general. But it's very important. One of the most important things in statistics is being able to interpret the calculations that you do. And so we need to talk about that. So again, for my 95% confidence interval, we found the form of this interval by looking at this probability. So we worked out that probability, that interval there. And we could do that because we were considering x bar to be a random variable. So remember, x bar had that normal distribution And that, again, that just means that it's a random variable, right? So it could take on any possible value, but it's going to follow the distribution of a normal distribution. Okay, so that's, again, this is all still kind of before we do the experiment, but then after I do the experiment, if I actually collect some data and find the sample mean, so once I substitute a fixed value, again, we'll use this lowercase x bar. So this is a fixed value. This is a random variable. Then all randomness disappears. So there's no longer, you can sort of no longer think about a probability statement like we did up there. So once I plug in a value of x bar, again, there's sort of no randomness going on. I know exactly what x bar is. I know what n is. I know what, again, I'm assuming I know what sigma is, and I have no randomness. And so what that means, so this implies, so if I plug x bar into this interval up here, if I plug my observed value in, and do that for the top number as well. What is that thing going to be equal to? Any ideas? Again, it's a probability statement, but I have no random numbers in there.
It's a range.
It's a range?
An interval? I don't know.
An interval?
0 and 1.
It would be 0 or 1. Why do you say that?
Because either it contains the mean or it doesn't.
Exactly right. So the response was this will either be 0 or 1 because either mu falls between those two numbers, in which case the probability is 1. That's like saying probability that 2 is between 1 and 3. Well, that's always true, right? Or we will miss or the true value of mu will not fall in between that interval, in which case the probability is 0. So this is either 0 or 1, and we don't know which. So that probability is either 0 or 1, and we don't know which one it is. So you might wonder, so what does that mean? So this leads us to sort of a different way of thinking about, or this motivates, I guess, how to interpret a confidence interval. So a correct interpretation of 95% confidence sort of relies on sort of a long-term behavior of this thing. So if we let A be the event that the mean is between my confidence bounds, and then I do the experiment over and over, so I do this experiment 10 times, 20, 30, 100, 1,000 times, then the correct interpretation of that 0.95 is that if I do this thing over and over, that's sort of the limiting probability that I catch the true value of mu in between that interval. So that probably makes lots and lots of sense, but maybe a picture will help a little bit better. And this shows each one of these lines here represents a confidence interval. So this is a simulation where I actually know what the mean is. So here's the true value. Here's the true value of mu. And each one of those lines represents the range of a confidence interval, of a 95% confidence interval. And so if I have 100 intervals here, I have 1, 2, 3, 4, 5, 6, 7 of those intervals do not contain the true value of mu, right? So the other ones, again, then this is a very artificial situation where we can say we know what mu is, simulated data. So what this says is that 93 of these 100, or 93% of the intervals, capture the true value of mu. Okay, and so if I did 100 more and kind of kept doing more and more of these things, the idea is that eventually, sort of in the limit, I would have 95% of my intervals would catch this true value of mu. So in the long term, (95%) will contain the true mean mu. Okay, so what's the takeaway from this? Again, what I put in your notes, I said the confidence level is not so much a statement about a single interval. Instead, it talks about what would happen if we did this thing over and over. So the main thing to keep in mind is that the confidence level sort of tells us about a success rate of the interval. So it sort of tells us overall how successful, sort of in the long term, if I do this thing over and over, how many times will I catch the true value? So it's more of a success rate, and it's not at all a probability. So this is kind of the main thing to take away, that the confidence level is sort of telling me about the success rate of a confidence interval. Okay, so we've been talking for a long time here. Let's go ahead and actually do an example here and see about applying this, and then we'll also talk about a very specific way to actually interpret these things. Okay, so now suppose that I have a random sample of 50 bottles of a particular brand of cough syrup, and spring break, so let's talk about alcohol, right? The alcohol content of each bottle is determined, and we have that an average of these 50 bottles is 8.6. And if we let X be the alcohol content in a single bottle, we're going to assume that the distribution of those things are normal with mean mu and variance 8.35. So what do we have here? We have a random sample here, x1, x2, all the way up to x50. I have 50 of these things, n equals 50. And I'm saying that these are IID normal with mean mu and variance 8.35. Okay, and my sample mean here, so my sample mean, x bar, which is just the average of these 50 observations, I'm told is 8.6. Okay, so that's just kind of being very clear about what the problem is telling us here so far. Okay, so then what we want to do is we want to create a 95% confidence interval for the mean alcohol content, and then we want to make sure to give a good interpretation here. Okay, so I guess previously in chapter 6, the question that I might have asked you is, what is a good estimate for the mean alcohol content of these things? In which case you would have either done method of moments or maximum likelihood and found that x bar, remember this is a normal case, so x bar is the maximum likelihood estimate. Now we want to, instead of giving just one number, we want to give a confidence interval. We want to give a range of values to kind of better assess sort of the precision or the accuracy of my estimate. Okay, so before I can do this confidence interval, I need to check two things. Remember, there are two conditions. I need a IID normal, and I need a known variance. And again, we're told both of those things are true, so we're good to go with our conditions. We have IID normal, and we also are told what our variance is. Okay, so then my 95% confidence interval is just as follows. So I can take the sample mean x bar plus or minus z sub alpha over 2 times sigma over the square root of n. So So my sample mean I found was 8.6. My z sub alpha over 2, I'm still talking 95% confidence, so I still have 1.96 there. So 95% confidence. And then I'm going to multiply that times my standard deviation. So let's say sigma is the square root of 8.35, or that's 2.89. So times sigma, which is 2.89, divided by the square root of my sample size, 50. Okay, so if you work that out, that'll give you 8.6 plus or minus 0.801. Okay, so then my 95% confidence interval I can say is 8.6 minus 0.801, and 8.6 plus, or approximately 7.80 and 9.40. Okay, so calculation's pretty straightforward there. Okay, and so now, okay, let's write down our confidence interval was 7.8 rather, up to 9.4. So now we want to let's think about how to interpret this interval. So I've calculated that confidence interval. That's great, but what does it mean? So let's talk about that. So the way that we will interpret these things, and the way to always interpret a confidence interval is as follows. So we'll say we are 95% confident that the true average alcohol content and then we'll say that we're 95% confident that is between those numbers that we found. It's between 7.8 and 9.4. Okay, so again, we're saying we're 95% confident that the true alcohol content, the population alcohol content, is between 7.8 and 9.4. And this would be a good thing to, this is sort of a good template to use here. So sort of in general, when you're asked to interpret a confidence interval, what you should do is we are blank percent confident that sort of whatever you're talking about. So here we're talking about the true population alcohol content is between the two numbers that you find. So that is going to be sort of your way to think about how to interpret these things. So I'm a certain percent. I'm 95% confident here that the true alcohol content is between 7.8 and 9.4. Yes,
So
Matt.
we're doing that like shorthand notation with parentheses. Does it matter if it's parentheses or brackets?
No, it does not. So the question was, can you also use, you mean like that?
Yeah.
Yeah, that's totally fine too.
Okay.
Whichever way you want to write that is okay. Questions, comments on other notation things or the interpretation here? So again, I want to be very clear about what we did not say here, right? We did not say the following. So don't write this down. I'm just going to write down what we did not say. We did not say that we we did not say that the probability that the true population mean alcohol content being between 7.8, and 9.4 is 0.95. So I'm not saying that the probability that the mean is between these things, these two numbers, is 0.95. That is exactly the wrong way to interpret a confidence interval. So please never write that down. If you write that down on an exam, I might take off extra points. So we're not saying that the confidence interval is not telling us a probability statement about the population mean. Again, remember, it's more talking about a success rate. So that if I did this thing over and over, eventually I would get 95% of those intervals to contain the true mean. So stick with the sort of the 95% confident interpretation, and don't say there's 95% probability or 0.95 probability that this interval contains the true mean. That's sort of the exact wrong way to interpret these things in this setting here. Okay. Yes.
So in confidence, it's like if you do it enough times, it'll eventually happen like 0.95 times in the mean. Yeah,
right. So the idea was that if I do more and more confidence intervals, if I do this thing over and over, then out of all of those, 95% of them will contain the true value. Okay. Yes, sir.
I don't understand that last part. If it's going up to a 0.95% chance, why doesn't this indicate probability?
Yeah. So that's a great question. This is a very difficult thing to understand. I think. So this goes back to this right here. So if you said that the incorrect interpretation, you would say that you would write down that this probability equals 0.95. That's the wrong interpretation. So remember, the mean mu is a fixed number. We don't know what it is, right? But it is a single number. So it's either inside our interval or it's not. And we have no way of knowing in this setting. Because we don't know what it is. So that probability is not equal to 0.95 or whatever the confidence level is. It's either 0 or 1, and that's not really telling us anything. So yes, so we're not talking about a probability here. And yeah, this is a very very fine distinction here. I think this is kind of hard to understand, but keep in mind that when you actually plug in So before we wrote this, probability was equal to 0.95 because x bar was a random variable. But when you actually plug in a value for it, then the probability is no longer, there's nothing random about that interval anymore. Yeah.
So I guess like the difference is like how random between probability and confidence is, like since it's not random.
Right. So yes, the distinction is between a random variable and something that's not random, right? So when you actually calculate the sample mean, it's not random anymore. You know exactly what it is. Okay. I will get off my high horse and we can move on. But again, just keep in mind that this is sort of exactly the wrong way to interpret a confidence interval. Okay, so to finish off this example. Just sort of conceptually, if I instead wanted a 99% confidence interval, so before we had a 95% confidence interval, would that interval be narrower or wider than the interval that we just looked at? Wider, obviously, right. So it would be wider. Again, to be more confident. We need to include more values in our interval. So that's, you guys are getting that. I think a good way to kind of keep this in mind is think about if you were a field goal kicker. Would you be more confident about making a field goal in those uprights or in those uprights? So I can't kick a football, but if I could, I think I would feel more confident about the one on the right there. So a wider interval will give you more confidence in capturing the true value. It's kind of the idea here. It's the intuition. Okay. So thinking about confidence levels in general. So far we've only talked about 95% confidence intervals. The form of our confidence interval is as we've seen before, but now suppose, but of course we can have different confidence levels. So again, this is my distribution of x bar. Well, sorry, this is the distribution of z, so x bar minus mu over. So again, this thing is centered at 0. And what we already found was that if I go out here to 1.96 plus and minus 1.96, I get a probability in here that is 0.95. Okay, but I could just as easily, again, if I'm interested in a different confidence level, if I go maybe from here to here and find two numbers such that I get maybe 90%, you can look up in the z table and find that these numbers are negative 1.645 and positive 1.645. And then maybe one other one to list on here. If I go all the way out to here and get such that I capture 99%, the critical value up here will be 2.576 and negative 2.576. So I have three standard confidence levels, and those are 90%, 95%, and 99%. And so for each of those intervals, here's the critical value that you want to use. So in general, I could ask you for any confidence level, so 85, 92, whatever. And you could find the critical value by doing kind of like we did for 1.96 earlier. These are going to be sort of your standard confidence levels that you'll use, and so therefore you can kind of use one of those pairs of numbers down there. Okay, so that's if I want a confidence level that's different than 0.95. Yeah.
Can you say that the difference between the 99% and the 95% confidence level will vary by this amount of percent?
Yes, you could. Right. So you could say, so in general, the 99% confidence interval, do I have another color here, will be between, so in terms of the standard deviation, it'll be that much larger, that percent larger, yeah, between a 99% and a 95%. Mm-hmm. Yeah. Okay. One more thing to talk about here. Finish up this little section here. One other definition to give to you is this thing called the margin of error. So that's the half width of a confidence interval. It's calling my margin of error. So how far off am I, or how much error am I giving myself here? So here, so far, the margin of error is just part of this one half of that interval, which is z sub alpha over 2 times sigma over the square root of n. So that's half the width of my interval is that part that I'm adding and subtracting from my sample mean x bar. And I think we're going to call this E. So that's going to be my margin of error there. Okay, so suppose that I'm in the planning phase of this thing, and I want to figure out the sample size I need to give me a particular margin of error. How can I do that? So if I have not yet collected information and I want to make sure that I can get a certain margin of error, we can do that sort of as follows here. So the margin of error again is, so again, the margin of error E is this z alpha over 2 times sigma over the square root of n. And I can solve for that in terms of the square root of n. And I'll get this thing as follows. So that's z alpha over 2 times sigma over the margin of error. So if I want to find a particular sample size based on a margin of error that I want, I can do so as follows here. So that's just showing you that formula there, I'm just sort of rearranging that plus or minus part. Okay, so maybe one more thing to say quick about our example. So we've already calculated our confidence interval, but let's say we're going back and instead of so how many samples would I need to have taken to get a width of my interval to be no more than 1? So how large would n have had to be to everything else staying the same, such that I want the width of my confidence interval to be just 1? So if the width is 1, then the margin of error E would be 0.5. So I want the half width of this thing. So then the required sample size to get that margin of error would be this formula that we had on the previous page. So z sub alpha over 2 times sigma over the square root, over the margin of error squared. So for 95% confidence, my critical value is 1.96. My standard deviation is still 2.89, and now I want my margin of error to be 0.5. And if I calculate that out, it gives me 128.3. So I don't know if you can find 0.3 of a person out or 0.3 of a sample out there. So we need to round up here. We round up and use n equals 129. And so you always here want to round up. So if I wanted my margin of error to be 0.5, then I would need to have taken 129 samples instead of just 50. So the sample size you can control how big your margin of error is there. Okay, that's it, guys. Thank you so much for being here. Have a great spring break. We'll see you in about a week.
Okay, I have 2 questions.
Okay, let me stop this real quick.